Your furnace and air conditioner exist because the heating industry hid the fact that the dirt under your house already does both jobs for free. That dirt sits at 52 degrees year-round, 6 ft down. In July, it drops your incoming air 30 degrees before it ever reaches a vent. In January, it warms that same air 20 degrees before your furnace ever kicks on. The whole setup costs $500 and runs on a single recovery loop your contractor pretends doesn't exist. Researchers in Greece proved the math worked in 1994. Canadian engineers built a house that needed no furnace through a brutal prairie winter in 1977. None of this is theoretical. Your air conditioner doesn't cool, it moves heat. And there's something already sitting under your foundation that moves heat better, cheaper, and forever called the soil battery. First off, every air conditioner on Earth is a heat pump running in one direction. Your central unit doesn't generate cold. It grabs warmth out of the air inside your house, ships it through copper coils, and dumps that warmth into the air outside. That dumping step is where the whole industry breaks. On a Phoenix afternoon, your condenser coil tries to push heat into 115-degree air, and physics doesn't let you push heat uphill without paying for the climb. 150 degrees. That's how hot the refrigerant inside your condenser coil runs, while it tries to shove that heat into air that's already scorching. Your air conditioner always loses that fight, which is why your bill doubles in July. The soil battery solves the dumping problem at the source. 6 ft below the ground, no matter what's happening up top, the dirt is sitting at 52 degrees under. That number doesn't move. It doesn't move when the air is 110 outside. It doesn't move when the air is 20 below. Sun heats the top inch of soil every day, but that energy never reaches 6 ft down. Soil conducts heat about as well as concrete conducts electricity, which is to say, barely at all. Below 3 millimeters, the temperature is what physicists call the undisturbed ground temperature. The dirt under your home is a thermal reservoir the size of every basement on the block, sitting at a constant 52 degrees, doing nothing all year. A buried 4-in pipe takes outside air, drags it through that reservoir, and hands you air that's already given up most of its heat before it reaches a register. Greek researchers Mihalakakou, Santamouris, and Asimakopoulos published the model in 1994 in Energy Conversion and Management, varying pipe length, pipe radius, air velocity, and burial depth. The numbers they got back matched the cooling every Persian wind catcher delivered thousands of years ago. The pipe does the work your air conditioner pretends only Freon can do, and the pipe runs on the heat reservoir your house is already sitting on. There's a reason the Persian engineers buried their cooling channels at exactly the depth where the soil temperature stops fluctuating. They didn't have refrigeration math. They had 1,000 summers of trial and error. And trial and error always lands on the same physical truth the engineering papers landed on thousands of years later. The soil battery isn't new technology. It's the technology your air conditioner was built to obscure. But here's the part that turns a summer-only trick into a year-round system. You're probably thinking, fine, a buried pipe is great in August, but what happens when January air hits the same pipe? The answer is that 52-degree dirt is now warmer than the air, and the same pipe preheats incoming air 20 degrees before your furnace ever wakes up. That single fact already cuts a winter heating bill in half. Your furnace only has to cover the gap from 52 up to 72, not from 20 up to 72. Now, bolt on the second piece, the part the heating industry treats like a secret, and the system goes from cutting a bill in half to nearly erasing it. The piece is called a counterflow recovery loop. The technical name is heat recovery ventilator. Inside is a flat plastic core, with 2 air streams crossing past each other, separated by thin aluminum or polymer plates. Warm, outgoing air gives up its heat to cold incoming air through the plate without the two air streams ever mixing. Sensible recovery efficiency in a residential unit runs 60 to 90%, and a good counterflow core lands around 80%. That's the heat your warm bathroom exhaust hands back to the incoming January air. It all happens in a small box, bolted in your duct chase, with no compressor, no refrigerant, and no moving parts beyond two small fans. So, picture the whole system in winter. 20 cutters outdoor air enters the buried pipe. The soil battery hands it 22 degrees of free warmth, and it exits the pipe at 42 degrees. That 42-degree air then enters the counterflow loop, where 80% of the heat in your 70-degree exhaust air transfers through the plate. The incoming air leaves the recovery core around 64 degrees. Your furnace's job just shrank to lifting that air the last 8 degrees to 72 instead of clawing it all the way up from 20. That's roughly a 6-fold cut in the heating load your furnace ever sees. Now, run it the other way for summer. 100-degree outdoor air enters the pipe. The soil battery cools it to roughly 70 degrees. That 70-degree air enters the recovery core and picks up almost none of the heat from your 68-liter exhaust because the gradient is tiny. It arrives at your supply register at 68 to 70. Your air conditioner's job just shrank from cooling 100-degree intake to barely tweaking a 70-degree intake. 2 pieces, 1 pipe, 1 box, 1 airflow direction that flips with a damper twice a year. The counterflow geometry isn't optional, by the way. A crossflow plate gets you maybe 60% recovery. A genuine counterflow plate pushes past 80. The difference is whether the warm stream and the cold stream pass each other end to end or only briefly cross. Counterflow means the coldest part of the incoming stream meets the coldest part of the outgoing stream, and the warmest meets the warmest. The temperature gradient stays steep across every inch of plate. That's the geometry the residential industry quietly never adopted. Now, here's where the story gets uncomfortable for anyone who's ever paid a furnace installer. Counterflow heat exchange isn't new physics at all. Engineers have built countercurrent heat exchangers since the 1800s, and the residential air-to-air version has been sold since the 1980s. The Greek research from 1994 reduced the buried pipe design to a single set of equations any heating engineer can solve in an afternoon. Researchers in Algeria, the Middle East, and across Europe have published measured results confirming the math holds in their climates. The reason your contractor has never mentioned this comes down to money. The residential heating industry in North America earns its living on furnace replacements and condenser swap-outs every 12 to 15 years. A buried pipe with a recovery core lasts longer than the house. There's no service contract, no compressor replacement, no annual coolant top-up. The whole industry's revenue model collapses if customers stop calling. The system also threatens the trades model. Installing a buried pipe is trenching work, not licensed heating work, and the recovery core bolts in for anyone who can read a wiring diagram. Building codes in most American jurisdictions explicitly allow earth-coupled ventilation, but the permit still runs through a licensed contractor. And that contractor has no reason to push a system that earns him no recurring revenue. The result is that the entire residential market in North America moved toward a central furnace, a central air conditioner, and a one-way bathroom fan. The counterflow loop and the soil battery got buried in academic journals and government efficiency programs that homeowners never see. That's not conspiracy framing. It's what happens when the people writing the consumer guidance are the same people whose paychecks depend on the alternative staying invisible. So, the cheap version, the one any homeowner with a shovel could install, stayed off the showroom floor, while the $10,000 furnace and air conditioner package became the default. That's the real reason your neighbor pays 20 times as much For a machine that does a job, the dirt does for free. You're probably wondering whether anybody actually runs this system in the real world, or whether it's all theory in a Greek physics journal. A National Research Council engineer named Harold Orr settled that question in 1977. His team built a house in Regina, Saskatchewan, with one of the first air-to-air heat exchangers ever installed in a home. It ran through a full prairie winter, with no furnace at all on about $30 of electricity a year. Winter nights on that prairie routinely dropped to 20 below zero. That house went on to inspire the German passive house standard, which an Austrian physicist named Wolfgang Feist formalized in 1993. Every passive house on Earth now requires a heat recovery core that hands back at least 75% of its exhaust heat. Many of the early European builds fed that core with a buried intake pipe. Canada's national R2000 efficiency standard has required a heat recovery ventilator in every certified home for decades in some of the harshest winters on the planet. The real-world numbers back every piece of it. A field experiment at Biskra University in southern Algeria ran a buried pipe through a desert summer. It recorded incoming air dropping more than 15 C, close to 30 degree F, with nothing but soil doing the work. That pipe stretched 56 millimeters and sat 3 millimeters down. A separate study published in 2022 measured winter intake air climbing more than 12 C through the same kind of buried pipe. These aren't lab numbers. They're measurements from occupied buildings in climates ranging from subarctic Canada to the North African desert. And they line up with the model the Greek researchers published in 1994. The reason American homeowners haven't heard of any of this isn't that the research doesn't exist. Those findings sit in journals like Energy and Buildings and Solar Energy. The people summarizing them for the homeowner-facing press happen to be the same trade associations that sell furnaces and condenser units. And the path from peer-reviewed research to your local home improvement aisle runs straight through the companies with the most to lose. You're probably thinking, this sounds too good to actually build in a weekend. And that's the part that surprised me too. The full build is 2 trips to a hardware store and a rented mini excavator. The buried pipe is 100 FT of 4-inch smooth wall drainage pipe at roughly $1.50 per foot. Pipe cost runs $150. Trench rental for a day runs $100 to $150 depending on your region. End fittings, a slope-graded condensate drain, and a coarse intake filter add another $50. That's $300 for the soil battery side. The new piece is the recovery loop. A budget single-room recovery ventilator with 2 integrated fans runs between $150 and $200 on the standard online suppliers. Total bill of materials lands at $500 on the low end. That budget core recovers around 70% of your exhaust heat, not the 80 or 90 a premium counterflow unit hits. 70% for $200 is still most of your winter bill gone. A pro install adds $1,000 or more if you want it ducted into your main air handler. For a single-zone setup, the homeowner work is digging a trench, gluing pipe joints, and screwing a small recovery box to a wall stud near an exhaust point. The trickiest piece is the seasonal damper. 2 manual butterfly dampers, one at the intake and one at the supply, get flipped at the spring and fall equinoxes to reverse airflow direction through the recovery core. Some installers automate the flip with a small 24V actuator wired to a thermostat. The system has no compressor to fail, no refrigerant to leak, and no part that wears under load. The pipe sits in the dirt for the life of the house. The recovery core has 2 fans that get replaced every 15 or 20 years for under $100, $500 up front, almost nothing after, and the year-round bill collapses to whatever you spend running 2 small fans. Together, they draw about as much power as a pair of old light bulbs. There's one detail worth getting right on the trench. slope the pipe 1/4 in per foot away from the house. Any condensation that forms inside it in summer then drains to a small gravel pit at the far end, instead of pooling under your foundation. Put a sealed clean-out cap at both ends so you can rod the pipe out every 5 years if leaf litter sneaks past the filter. Wrap the recovery core in 2 in of rigid foam insulation to keep heat from bleeding into the surrounding wall cavity. Those 3 details are the difference between a system that runs maintenance-free for 30 years and one that needs an annual visit. The tighter and better insulated your house, the closer you get to the Saskatchewan result of no furnace at all. A drafty house still wins big. It just keeps a smaller furnace for the coldest nights. The other detail homeowners get wrong is pipe diameter. 4 in is the minimum that delivers enough airflow for a typical bedroom-size zone. 3 in pipe looks tempting because it costs less and digs faster, but it strangles the airflow and cuts the temperature transfer to 1/3 of what 4 in pipe delivers. 6 in pipe is overkill for a single zone and adds excavation cost without adding much performance. 4 in is the sweet spot the Greek model identified and every subsequent measured study confirmed. The pipe also needs to sit on at least 4 in of compacted gravel to handle ground settlement without sagging into a low spot where water collects. Trench depth matters too. 3 ft of cover is the bare minimum. 4 to 6 ft is where the soil temperature stabilizes enough to deliver the full effect. Anything shallower lets seasonal soil temperature swings bleed into the pipe and ruins the year-round consistency. That's what happens when you stop fighting physics and start using the heat reservoir your house was already built on top of. If this revelation about the soil battery changes the way you look at the energy potential beneath your feet, please subscribe and like the channel. We are dedicated to uncovering the engineering truths that have been kept in the shadows. Let's cultivate a more efficient future together. Our next investigation into hidden technology will be released soon.